So 443. So that allows you to send 3 units. So now you have this graph. So now you're sending 3. Originally this was 1, now it has become 4. This was 2, this became 5. And you look for a path. There is still a path, right? Oh, this. Oh, okay. So there's still more capacity this way. So you find that path and push, one more unit through that path, and that gives you a graph like this. And you can see that there was this edge that was there before has disappeared because you originally first time you send the traffic down, other time you send the traffic up. Now the two are cancelled out, and there is still a path, right? SBDT, and you go through that, and now you can see that at this point there is no path from S to T. Okay, in the residual graph, you can see that there is no way to go from S to T anymore. Okay, so this algorithm is called max flow min cut because you can, if you think of a graph like this, you can draw a line through this, right? Now, whatever flow, you draw a line through this so that S is on one side and T is on the other side, right? So whatever you're pushing from S has to cross this line, right? So the maximum you can push through should be less than the maximum of these 3 edges, right? Not the maximum, the sum of those 3 edges, right? So there can be many ways to cut this graph, right? So the constraint applies regardless of how you cut it, right? So that means there is this notion of a min cut, which is the cut that has the minimum capacity, and what you can intuitively see is that the maximum flow you can push through is limited by the minimum cut, right? Because the flow has to go through the cut, right? So that's why it's called a max flow min cut algorithm. Okay, so that's a theorem. It says the size of the maximum flow equals the capacity of the smallest cut. Okay. Now, what is the runtime? So each path finding takes some amount of time. So if you use an algorithm like BFS, it's going to be linear time. Okay, and the adjustments, right, to the graph to compute the new residual graph can be done in the same time, because once you find a path, then all the adjustments are related to that path, right? So you don't have to change anywhere else. So the residual graph can be computed within the same time, and if you do a simplistic analysis, then you can say each iteration adds at least 1 unit of flow, right? Then the cost becomes C times E, where C is the maximum flow that you can obtain. Okay, but this is not a linear time or polynomial time algorithm, right? Because the cost can be exponential in the input quantity, right? Because so this is not a good algorithm, but one can show, but we won't. One can show that if you use an algorithm like BFS, then the number of iterations is going to be limited. So you will have an algorithm that is V times E rather than something that's proportional to the total cost or the total flow that you're going to be able to push through. Okay, so this is basically a relatively efficient polynomial time algorithm for doing this max flow. So the last thing I want to do is to talk about how you can apply max flow to this problem called bipartite matching. Right? So what is bipartite matching? You have what is called a bipartite graph. That is, you have a graph where you can separate the vertices into two subsets, right? Here, it's convenient to draw one subset on the left and other subset on the right, and all edges are between vertices in the two sets, right? So you cannot have vertices within each set. Edges within each set. All edges have to cross, right? So this is called a bipartite graph. A matching in a bipartite graph is, so although let's say Al here could be paired up with any of these four girls, a matching is one that just picks one of those pairs, one of those possible pairs. Okay, so matching is like finding a match. Let's say they want to dance. Well, then you want to find one boy, pair the boy with the girl. So that's why this picture is here, right? So that's the kind of matching that we want to do. And the perfect matching or maximal matching is one where you pair as many vertices as possible. A perfect matching is one where everybody is matched. Okay. So you can see, we'll come back to this again next time, but you can solve bipartite matching using MaxFlow MinCut by introducing this source and a sink, and saying that from each source you can send one unit to each of the elements here, and then from each of these vertices you can send one unit to T, okay, and then saying that the capacity of each of these edges is 1. Okay, now whatever MaxFlow algorithm will give you will happen to be the maximal matching. Okay, if you think about it, become clear. We'll come back to this and finish this up in the next lecture. Okay, so again, the point here that I want to conclude with is that MaxFlow algorithm can be used for solving many problems, and bipartite matching is one example, right, where a problem that on the surface doesn't seem related to MaxFlow, but can easily be modeled using MaxFlow, and that's really the strength of the MaxFlow algorithm, that many problems can be modeled in terms of MaxFlow. By simply augmenting the graph in a certain way, suddenly, if you solve a MaxFlow problem, then you have a solution to your the version of problem that you're trying to solve. Okay, let's stop here and continue on Tuesday.